Quick reminder that when somebody asks you a question, repeat the question so everybody who's watching the live stream can also hear the question.
Just one other announcement that I forgot. Apparently, there is going to be a survey and a subsequent raffle for some really good prizes. So every senior should have a link to the survey, and there will be some hard copies of the survey at lunchtime. So this is sort of an added thing that I've just been aware of. So at your convenience, please do the survey, and there will be some hard copies at lunchtime. Okay, we're now into session 2, medical health, mental and fitness applications. And the first team to present is Team 12, open source cytometry platform.
Yeah. Good morning, everyone. We're the open source cytometry platform team. My name is Thuba.
I'm Chris.
I'm Connor.
And I'm Greg.
So our project deals with malaria, which is a disease that 214 million people were diagnosed with in 2015. Approximately 500,000 people died, and 75% of those deaths were due to this strain of malaria known as P. falciparum, which can be fatal within 72 hours if it's gone undiagnosed and untreated. So our team aims to improve world health in rural, resource-poor areas by creating an affordable and portable malaria diagnosis tool that will offer rapid results and save lives. We have built our project on the research of Dr. Howard Shapiro, who has over 20 years of experience in this field. And now Chris will talk about current cytometers on the market.
Thank you. So just to come out clean and say what is cytometry, just so that you don't get lost in that detail. Cytometry is just the technique for diagnosis. It's counting of the blood cells. So that's our technique. So most cytometers are large and immobile. And if you look at this image, it's clear that it takes up a lot of space. It's heavy. It's not meant to be moved. And these devices could cost anywhere from $7,000 to $40,000. So they're definitely not cheap. And the results aren't rapid. It could take more than a half an hour to get your results. So how is our product different, our cytometer? So our cytometer is portable, meaning that it's powered off of battery, and it's also lightweight. Oh, okay. It can be easily transported, so it's easy to carry. Thank you. It's inexpensive, meaning it costs less than $2,000. And that's the cost that it takes to build a real engineering solution that can diagnose, not just some free app. We need something that could actually go out in the field and be used. It's a rapid diagnosis, meaning that it takes less than 15 minutes to come up with results. And our device actually does it in less than 10. And it's open source and open hardware, meaning all the code's online and all the parts can be readily accessible online. And there's a lot of communities and support groups behind that, as well as we provide our own documentation to be able to set everything up. So now we're going to play our video. There you go. Our device is quick to set up and operate. Yeah, so Connor's just setting up the device right now. And it takes less than a minute to put together, and it's basically just plugging in 3 cables, so it's not hard to set up.
The clinician simply loads the blood sample on the slide and places it under camera.
And here Connor's mounting the battery to the side. It sticks right on there.
From there, the user has options to select from the home screen whether they want to run a quick diagnostic test or calibrate the device. The user receives feedback on the screen of the current status of the sample. Finally, when the results are determined, they will be displayed to the user in clear text. At the result, the clinician is ready for the next test.
So I'm not going to go too deep into the technical overview. This is our highest level of abstraction, but basically all you need to know is that we have our power system, right? Optical system, which is just the camera and the LEDs, the CPU and the user interface, which is just the LCD screen with the button.
Now, because this is an open source project where anyone can recreate this device, we had to eliminate all barriers to entry. So to do this, we chose to build our cytometer entirely from readily available parts, like Chris mentioned. For instance, the small, low-power computer here is widely available and costs just $30. And for the hardware development, I optimized the circuitry to minimize the overall size of the device, and I was in charge of power distribution. The battery you see here can power the device for over 4 hours, which means that a diagnosis test can be done anywhere. And this portability enables doctors to bring the clinic to the patient.
So here you can see the inside of our optics box on the right-hand side, which is, you see that small white table, which is where we place the blood sample under the cameras and the LEDs. And then on the left, you see Connor with the device all together, which is not more than 10 by 10 by 10. The electronics are mounted on top of the optics box, and everything actually fits inside the optics box when it's disassembled. And there's just a few cables that you need to connect every time you set it up. And then, as we've mentioned before, we have the open source documentation, which provides step-by-step instructions so you can recreate the device, both hardware and software.
Yeah, so I worked on the software part of it, and we developed most of the software. The actual diagnostic algorithm, that skeleton, was provided to us by our clients, the MD and the PhD, but we built everything else from the ground up, meaning we modeled all of our hardware as software, as well as built in some cool features on our own. So we basically spent the whole year perfecting our optic system and our imaging to reduce error, and making sure that we have, a pretty legitimate device. We also include some cool features, such as in the top right, the ability to store patient data to the SD card. We've also worked in the ability to detect if the device needs to be calibrated. So that means that, you don't have to worry about tweaking with the LEDs each time. You could detect if it's not calibrated, as well as the ability to automatically recalibrate it. So we have a program on the home screen that could do that, so the user doesn't have to worry about that.
Our project has a lot of image processing involved, where the goal is to extract meaningful and useful information from the raw images. The computer takes measurements of the blood sample using only pictures in order to find signs of malaria. All this is done through various image processing methods and techniques. We wanted to get our computer to do what a doctor would do with a microscope. We had to write software for the computer to communicate with the camera, in order to be able to reconfigure the camera's settings, tell it when to take pictures and at what exposure time, as well as receive pictures from the camera and store them for later analysis. We built a user interface so that the user can interact with the device. After they input a blood sample and select their program, the device updates the user with progress and and most importantly, displays the results of the diagnosis. Although we made considerable progress on this project, there's still a lot more potential for a device like this. One idea is to explore other hardware options. The most expensive part of the device is the camera. If one could make the device with a less expensive camera while still maintaining the same degree of accuracy, it would bring the price down a lot and make it more accessible in third world countries where people need it the most. As technology improves and prices come down, a device like this becomes more and more realistic. Another idea is a smartphone app to make it more convenient for doctors to get their hands on raw data. Finally, because this is a general blood analysis tool, with a little modification, it could be made to diagnose other diseases such as tuberculosis, and take other kinds of blood measurements. With a little bit more work, a device like ours could do a lot of good in poorer parts of the world.
A device like this has the potential to test hundreds of patients a week, and this is only the beginning. We have unlatched the gateway for the open source community to fight disease and work to improve global health together. So let's not stop here. Thank you.
Good work, guys. So I was wondering what if you did any statistics on this and done any probability of false detections, and how that compares with the current devices.
The stage that we're at, we're still testing on non-biological samples. Our clients have to like build the same device, you know, to verify that they can replicate the device easy enough. And then once we have that, then we'll be able to start testing on biological samples and determining like false detection rates.
So how are you testing it now to make sure that you're getting the right number of blood cells and things like that?
So I don't want to get like too into detail, but our goal right now has been to verify that these like non-biological samples are kind of like calibration samples, and we're just trying to get it so that just to kind of verify that our camera has, you know, the resolution and the depth of field and that kind of thing for us to actually like detect what we want to detect.
Sure, thanks.
So also, our algorithm does account for like bad clusters of samples right now for just the calibration beads, and also if there's like any dust or smears on that, we do have that built into the algorithm, so it just counts those as like bad areas, and it gives you a number of good areas and bad areas.
Cool, thanks.
Anybody else?
Yeah, over there.
So since you are working with biological samples and this is usually done in a lab, what are you guys doing to prevent contamination when this is being used in the field?
Yeah, so the question was, because we are working in biological samples, what are we doing for prevention, right? So I don't know if you picked up on Greg said, we're right now not using biological samples, but we do have like a spill kit and like a glass kit, and it would be in the proper environment. Yeah, they're in it? Oh, they're like fixed samples? Yeah, sorry. And they're also like inactive, so we're not taking, you know, like you could start with like a rat sample that has inactive malaria, something like that, and you know we could work with that so that even if it did break, it wouldn't like spread malaria to the engineering department.
So this is super cool. So you guys saw in there that you were storing the records from that. Is there like how do we get those out? Like, and is there like some sort of like privacy compliance things you have to do because you're holding on to like patient data that, you know, like Joe has malaria. I don't want to talk to Joe anymore.
Yeah. So the question was about storing patient data and I guess sort of the the privacy concerns. So that was just like a proof of concept type of deal. Right now they're stored to the SD card that's on the Raspberry Pi. But yeah, if we wanted to do something like transmitting data like through a smartphone, you know, maybe down the line we'd have to look at like encryption and maybe some, you know, ability to protect that. But at the moment, it would like you could grab that data by taking out the SD card and like backing it up. That was kind of the proof of concept behind it. But yeah, we haven't really like that's not real data. But yeah.
Just great.
Yeah.
Next team in this session is team number 3, DOSeye.
So we're Team DOSeye. I'm Ami.
I'm Alex. I'm Solomon.
So what is DOSeye? It's an optical finger probe. It will extract information from tissue, so it will have a source. It has a source and detector on it. The source shoots light through tissue, and the detector detects it on the other side. And with the detected light compared to the source light, we can extract information from the tissue, such as the hemoglobin concentration and how much oxygen a person might be utilizing in their body, which can have a lot of health indications. And we will also be able to store the data we do collect into a searchable database that can tag and store the data. So how do we use it? We start off with a phantom, which simulates human tissue. It's a silicon block. We put our detector and source on top of it. So our source is a vertical cavity surface emitting laser, or a VCSEL for short. It's that blocked out in the middle, and this is the PCB to run it. So it's connected to a current controller, which will put current through the VCSEL, and that'll shoot light out. And then our APD, or avalanche photodiode, is our detector, which also runs on a PCB. That requires a high voltage, so we have have voltage conversion from the wall into the board. So once all this runs, we shoot light out of the source into the detector through the tissue. And that data gets output into a network analyzer, which can measure frequency modulated signals. That goes into our LabVIEW code, which makes Bodhi pots and stores the data. And that goes into our searchable database, which tags the data and makes it searchable by those tags. So the high voltage converter PCB, the APD PCB, and the source all go into our housing, which has a hole for the source and detector, so you can put your finger on top of it, and that's shielded so you don't hurt your eyes. This is our project video.
Here is our DOSeye probe. Once the device is plugged in, simply flip the switch to turn on the power. The device can be used to take measurements through a finger or a silicone phantom. A LabVIEW software is used to control the currents for the laser outputs, as well as control taking the measurements through the detector.
With our software system, a user can add new data files to a searchable database, display tags that have been associated with files, and conduct queries, choosing to either display search results or copy them to a folder.
So for our probe, we needed to make a circuit board for our detector for APD. And so we used ExpressPCB to design the circuit board, basing it off of Hamamatsu's existing evaluation board. And we ended up rearranging the geometries of that board design so that the APD would be far away from the other components so that it could be placed flushed against a phantom or against the finger tissue. We made sure to impedance match the output traces with the SMA connectors, and the APD board has switches that allow us to adjust the gain settings between low and high gain, and the direct current feedback settings to allow it to turn on and off. And it takes 2 voltage inputs, 1 high voltage input, and a 3.3 voltage input, which we used keyed header pin connectors so that you wouldn't accidentally reverse the polarity on those. And then so we wanted our APD circuit board to be able to plug directly into a wall without needing any external large power supply boxes. So we ordered various voltage converters. We got an AC to DC wall adapter so it can go right from the wall socket. And then we got a couple of low voltage DC to DC converters and a variable output high voltage DC to DC converter, which we again, using ExpressPCB, designed another circuit board for, and it has a potentiometer on the board to allow for a variable output voltage of up to 200 volts.
So here we have a picture of our 3D printed housing from Epic,
it consists of 3 separate parts, which were all designed using SolidWorks. And as you can see, the VCSEL and APD are both mounted flush with the top of the probe. And in order to take a finger measurement, you would place your finger right here, and you would slide the housing down, slide the shielding down. That way, you prevent any risk of eye injury. And as you can see, we also have inputs from our current controller that connect to the VCSEL, and we also have outputs from the APD PCB. And we also have openings for the switches on the APD PCB so that we can change settings during testing.
So we had to do a lot of testing to make sure that the settings that we were running this at were correct and made the device as accurate as possible. So for the APD board itself, we had to find the operating voltage that we wanted to run it at. We found that to be around 165 volts without saturating the signal, but also getting a high signal-to-noise ratio. And then our optimal switch settings we found to be with background correction on and low gain. So our VCSEL board, we had to find what currents we wanted to run the different wavelengths at, and we found them to be 10, 5, 15, and 10 milliamps, and we used a modulation depth test for that. And then for the probe as a whole, we measured the average drift over 1 hour, so we took a measurement at the first minute, and then we kept taking it for 60 minutes. And we found that the deviation from that first measurement only went to 2%, so it was pretty constant. And then our average accuracy, we tested on all the different phantoms in the lab, so all the different tissue types, basically. And we got around 20% error from the benchtop golden standard that the lab had. And then our usable bandwidth we found to be about 50 to 450 megahertz. So this is a sample of something that we would get out of the network analyzer. So the top is the signal and the bottom is the noise. So you can see that the signal to noise ratio, it's in dB, so the amplitude is in dB, it's a Bode plot, and the frequency is frequency modulated, it's not the frequency of light. And it goes from 50 to 500 megahertz, and you can see that the signal is pretty far from the noise until about 450, and it starts getting pretty close, and it wouldn't be as readable around there.
So once data files are moved from the data acquisition machine onto the lab research drive, or like all clinical data is stored, the script goes through all files, extracting metadata from them. Metadata is stored in the file header. It contains information regarding its acquisition, like patient ID or source detector separation. It goes through all that information and associates that into a database. So for each file, an entry in the database consists of a file name, file location, tags and values for the file's metadata. And with a web interface, a user can then access that from any machine without the software having to be installed. It's running from the central server, and you could conduct search queries. Here's an example of the user interface. Something like this would be useful because in an actual clinic, you'd be collecting thousands of data entries. Being able to sort through those quickly and efficiently means that it would be easier for clinicians to look for data trends. So in conclusion, we have a working system and a means of efficiently sorting through data. Thank you.
I'm going to ask one question. You obviously have a non-invasive test. What kind of diseases might this be able to pick up?
Some of the things this might be able to pick up are it can detect hemoglobin levels, and it can also measure specifically from the spectral properties of the finger. You can determine the amount of oxygenated hemoglobin versus deoxygenated hemoglobin. So one of the things that can help detect is if someone is going into shock, for example, if some of their oxygenated levels are way off.
Yeah, so since it's non-invasive, it could be used constantly rather than something that would like poke you or anything like that.
So what I think I understand now. So you had the project testing results a few minutes ago where you said like you had 20% error rates inside the Phantom lab results. Is that good? Is that bad? Like I actually have no frame of reference, so I don't know if 20% error is good or bad.
Yeah, so it's not great. I think with more testing, we might be able to improve the accuracy, or it's possible that the APD is just not the detector to do this with. It hasn't been done before, so we don't really know until we built it. But hopefully we can get it a little farther down with a little more testing and a little more tweaking.
Do you know what causes the error, like where the error sources are coming from? Or
so before we had a lot of error from saturating the signal, so we oversaturated it. Our source detector separation, we were trying to get as close as possible, but it's possible that we might want to get it further. The housing is set right now, so it is what it is. But in the future, they could try to separate that to maybe reduce the risk of saturating the signal, if that's what's happening.
All right, so you guys are plugging this into a wall, and so is this meant to be like in a lab or like a hospital, just like bedside or something along those lines? Like what's the real life, use of this?
So this will be used in Professor Roblaire's lab in the biomedical optical technologies lab here at BU.
So what's limiting your usable bandwidth?
So because when you're getting upwards of 450 megahertz, the frequency, like the period's so small, it's really easy to throw off like the phase, and there's just such a small like margin of error, I guess.
Is it a measurement error?
Kind of. There's also like attenuation from the cables and stuff like that. So the noise is just, it's not really that the noise is amplified, it's that the signal is just really dipping.
Is that because of the impedance matching traces on the PCB?
Well, the impedance matching is supposed to help against so that it would reduce noise, and otherwise you might get reflections of it. So that could actually make the signal weaker, and just impedance matching helps because you've got the RF signals going through there, so that you don't like have any unnecessary noise.
What is the bandwidth of the impedance matching? Were you able to calculate that, or?
I don't think so, but I think most of the attenuation is coming just from the length of cables that we're using to connect these things together.
Okay.
The longer the cable, the more attenuation we're getting.
Thank you.
Okay, our next team in this session is team number 6, DORI, Door Opening Robotic Intelligence.
Thanks, guys. My name is Victor Weiss. This is Katie Lewis and Davey Huang and Jingning Zhang. And together we are the DORI team, also, aka the Door Opening and Robotic Intelligence team. So DORI is a result of a collaboration between the ECE department and the William E. Carter School of Boston. So our project seeks to provide students living with both intellectual and physical disabilities the ability to easily and safely open doors. So the simple fact is that like the modern door isn't designed for everyone, and can heavily impose on the quality of life of the more than 3 million wheelchair users in the United States. So modern doors require a large amount of strength and dexterity to operate, especially from a seated position. Often this level is of a level of coordination that's especially difficult to reach for students living with disabilities. So DORI is a system designed to bridge that gap and provide greater mobility and independence to students living with disabilities, but enabling them to open doors. So in particular, we were inspired to build DORI after meeting with one student, Norman, at the Carter School, who needed a way, limited coordination in his arms, and needed a way to safely navigate his home in the school. So I'm going to give it to Davey, who's going to explain our solution.
So our solution is a door opening attachment that can be placed on a wheelchair. It currently features the ability to open doors with door levers and push bars. It operates through a one-click detection mechanism to find the doorknob. And that way, the one-click mechanism allows a minimal skill threshold for use. Utilizing 2 rechargeable 12-volt batteries, we can have 2 hours of camera time, which opens up to 180 doors. And here's a quick video. Come check out our table for more detailed videos.
So now that you've seen our product in motion, we'll go through some of the technical details. So this is our system diagram, and it shows the relationship between all of our components. So a Windows 10 laptop is the central control of our system. We use processing to develop the GUI, and processing is an open source language based on Java. So once the user initiates the process by pressing the spacebar, a signal is sent to the Connect version 2 camera, which looks for a QR code. It reads what's encoded in the QR code and does calculations to find the real-world position of the door handle and the type of the door. And that information is passed through serial communication to 2 Arduinos, which control the linear actuator and the robotic arm. And our whole system is powered by 2 batteries, and the Arduinos and the Connect are connected by USB to the laptop. So as Davey mentioned, we wanted to keep our user interface as simple as possible. Many of our users have little to no upper body coordination. So rather than using a joystick or something to control the robotic arm, we wanted to make it as automated as possible. So we just require them to press the spacebar and the rest is automated. We have some optional features, so you can press the M key to toggle the mute and unmute of our audio safety feature, which alerts bystanders that the process is ongoing. And for the door detection, we chose to use QR codes. So our users will mostly be using the product in familiar areas such as their home and the school. So we require them to put QR codes on any doors they would want to open. And inside the QR codes, we encode the type of door, so either push bar or handle, the direction, so push or pull, and the distance in millimeters from the lower corner to the door handle. And the positive and negative indicate which side of the handle the handle is of the QR code.
All right. So encoded in the QR code, like Katie said, is a string with the distance offset from the lower corner of the QR code. But there's more information encoded in the QR code than just that. the little squares on the corners of a QR code are actually called markers. And by utilizing the Connect, we can actually get the real-world coordinates of those markers and use them to define the plane of the door. And from that, we can use the top two to create a vector that points parallel to the vector toward the offset to the doorknob. And then we can apply the known distance in the QR code string to the bottom marker to point toward the doorknob. And our system uses 3 GUI states that we start in the welcome state. And then once the user approaches the door they want to open with a QR code, they're going to hit space to enter the detection state. From there, it will search for the QR code. And once it finds it, it will automatically enter the action state and perform the the previously mentioned operation to get the real-world XYZ coordinates. And from there, it can send data to the arm and the actuators.
So like for the robotic arm to reach the door handle appropriately, there's a translation method needed to be performed. Here's in the picture is an example of a arbitrary example, like where it's in the where it's a side view. The red point is the destination where the robotic arm wants to reach. We will adjust the lower arm servo and the forearm servos in turn. In turns, like they align the robotic arm claw, which is on the terminal of the robotic arm, to the destination. And this operation is done for more than one times to minimize the practical errors. And this one is the top view of the same operation. As long as we are done with the previous slides, we are able to find the length of the arm that we need. So it's like only we need to move the base motor so that the arm can reach the destination in the 3D world, eventually.
So by this part in the process, the door handle has been detected. We know what type of door, which direction is flowing, as well as, and the door handle has been unlatched if there is a door handle. So at this point, we used 4 motors on the wheelchair to do all the heavy lifting of the actual door. So on each side of the wheelchair is a linear actuator, and at the end of the actuator is a gear motor, which turns the hook you saw in the video, which is capable of hooking the door for the pull action. So to control all 4 of these motors, they're all 12-volt DC motors. So we use an H-bridge just to flip the direction of the current, which then can extend and retract the actuators or lower or raise the hook. And then all this is controlled with an Arduino. So it listens through USB for a selection from the laptop to which procedure to run, whether it's like a right side push or a left side pull, however. And then the Arduino executes that by switching the GPIO pins, which control the H-bridges, which manage the motors. So another this picture of our system you saw in the video. It's all built mainly out of aluminum. Some of the features we have a little rail system, which the linear actuator slides the carriage on, which does the pushing and pulling. There's also a camera stand, a laptop, and also the whole design is strapped only to the handlebars, and then there's a support structure in the middle there. Oh, okay. Basically, it's portable, so it can be removed very easily.
So after our customer installation, Professor Ashik is pretty happy with the result, and DORI will be an ongoing project, and next year we will have another team to be able to expand the DORI to have more interesting features like elevator button push and card swipe informations. And that's it, our project. Thank you. Any questions?
Will this device work on any wheelchair?
Short answer, yeah. So it'll fit on the most standard ones. The only thing that'll adjust may be the width, which is a pretty common customization, but where it attaches on the frame are easily slidable. They're just bolted on, those bolts can slide easily. It's on the T-slided framing, so it's pretty much adjustable to any standard wheelchair, yeah.
Thanks.
I
think you mentioned this, but so the QR code has to be put in a very specific place on the door.
Yeah, so we have encoded the distance from the lower corner to the door handle. So for customer installation, we would measure that out and put it there, and it would just stay there. So it's a one-time measurement, and then, yeah.
Would this work for door handles that are kind of the twist type, or is it all for the pull down?
So for our project, we are aiming to do the handle and the push bar. So we're working with the Carter School, which is a public school for handicapped students. And we checked all of their doors, and they have those two types, so we tackled those two first. But it would be easily, you would just change what's encoded in the QR code and a few commands for the linear actuator and the robotic arm.
Okay, thank you.
Those two types, as you see right here, like the lever arm is actually the most popular kind of door handle in the United States right now. The door knob itself is like phasing out, and the lever is the push bar and the lever are actually the most common. So.
Okay, thank you.
This is super cool. I love like the whole system working together. Have you guys thought about the hardware that you need to power this? Like, it looks like you have like a really gigantic, like super beefy laptop. Like, could I run it with something that's not as beefy, not as pricey?
Currently we're using the Connect 2 camera because it has a very good depth sensor, somewhere around millimeter accuracy, I believe. Due to some limitations with that, we had to use a Windows 10 computer.
But I mean, like the GPU, like, are you GPU bound? Are you CPU bound? Like, where could I scale on that laptop to save money?
So the GPU requirement is actually the fourth generation or fifth generation of Intel GPU processor. So it's like pretty low cost kind of. So like if any computers with a independent display card is able to support this feature.
From the audience? Over here.
What have you done to stabilize the wheelchair so it doesn't tilt over when the arm reaches out and twists?
No. So, sorry. She was asking about stability during the process. How do we make sure it doesn't like twist or turn or doesn't like rock in any way? This is how do we stabilize the wheelchair? All the weights kind of when you're sitting in there, you actually have like a very high, low, very large, low center of mass in it. It's very hard to like rock the wheelchair at all. And also, there's hand brakes on the wheelchair that that are very easily just like press down, and that locks the wheelchair into place, and it's unable to move during the process.
So when we were planning out the design, we were worried about that too, about it twisting this way or like pushing back when the door is being pushed forward. But during our testing, we haven't found any problems with that. The weight of the person is enough to stabilize it.
Have you guys tested in low light conditions?
Sorry?
In low light conditions, say the light turned off in the room, does your whole system work in that condition?
So we haven't tested it with no light or very low light. I think it probably wouldn't work, but one solution would be just to add a small light where the robotic arm is to flash on the QR code. We've tested it with different type of lighting, but there's always been light. Yeah.
And it works for different types of lighting?
Yeah, and it works from quite a few angles as well and distance.
Thanks.
Yeah, so we tried to make it so that it doesn't interfere with the student's normal wheeling procedure. So you can fit your arms like within the frames. You don't have to like go over it or anything. So it doesn't really interfere.
Yeah, at this point they're locked in at about 50 inches from the back of you to like out in front of you, and that's a limitation of the current state. Yeah.
Okay, all right, thank you. At this point, I think everyone here should have recognized that all of the projects that we do in this department have an important societal impact, all striving to make the world a better place. The next team, Tidemark, is one of 3 projects this year that were student-defined. Typically, we have projects which come from companies, faculty, alumni, and the students then essentially implement an idea provided by a client. This year, we opened it up to a competition for student-defined projects. 3 were selected. This is one of them, Tidemark. So without further ado, let me introduce Team 22, Tidemark.
Thank you, Professor. I'm Zach.
I'm Sam.
I'm Anna.
I'm Alex.
And I'm Becca.
And we are Tidemark. And I wasn't initially planning on sharing the background and how we came up with this project, but since Professor Pisano gave such a great introduction, I figured I'd share. I was traveling abroad over in Spain with my good friend Amber, who has type 1 diabetes. And traveling abroad, you spend a lot of time with a person. Like, we were together for the majority of the time, about 2 weeks straight. And I really got up close and personal with what managing type 1 diabetes is like, and how hard it is, and how it disrupts the very, very subtle things that we all take for granted. Is we really take it for granted. It's not guaranteed. So just small changes, checking your blood glucose, having to stop, going for a hike, going back to get a snack. These are all problems that we're trying to solve with this application. So for the background, what is type 1 diabetes in the first place? Type 1 diabetics, they don't produce any insulin. Insulin is a hormone typically secreted by the pancreas that converts glucose into energy. And that in healthy adults is managed automatically through the pancreas, and typical ranges of blood glucose levels, and that's the important metric for this presentation. Blood glucose levels are what type 1 diabetics have to manage manually. For healthy adults, this is managed automatically by the pancreas and typically range from around 80 to 100 milligrams of glucose per deciliter of blood. The American Diabetes Association suggests that type 1 diabetics stay within 80 to 130 milligrams per deciliter. When you start going very, very high and very, very low on that range, you start having very serious long-term and short-term complications. If you're in the higher end of the spectrum for a long period of time, this can cause cell damage and leads to nerve damage, kidney failure, and heart disease later in life. Much higher probability. When you go low, immediate consequences such as seizures, loss of consciousness, and even death. This isn't including how you feel throughout the day. Again, it's converting glucose into energy. So without that procedure, you feel groggy. It's hard to think throughout the day. And it really, really impedes progress in just living a normal life. So the current solutions out there on the market today, there's a lot of hardware, there's a lot of software, and it's a lot to keep track of. Your data is, all the data is there. There's a lot of cool products. There's Fitbits, there's continuous glucose monitors. All this stuff exists, but it's in all these different locations. It's hard to manage, and it's hard to keep track of all in one location easily. And so that's our goal, is to help type 1 diabetics stay healthy without disrupting their day-to-day life. And so how we accomplish this is 2 steps. We automatically collect and display user data relevant to blood glucose levels, and then we predict future ranges of blood glucose levels. This is in order to improve type 1 diabetics' abilities to self-medicate, so you can see your trends in real time. You can analyze them over the past week or so, and you can start making changes in keeping within a safe range more consistently. And you can also prevent unsafe blood glucose levels due to our prediction algorithm showing you if you're going very high or very low in the next hour. This leads to a healthier and safer life while minimizing daily disruptions. And we have a video illustrating our project in action. Tidemark enables type 1 diabetics to live healthier while minimizing daily disruptions. Tested in the field for a month, Tidemark is streamlined and easy to set up. Interfacing with existing hardware and software is as simple as flipping a switch.
After that, Tidemark will automatically start conglomerating user data and is ready to use. For quick insights, Tidemark's main graph displays all relevant data influencing blood glucose levels in one simple chart. To record a meal, simply click on the Quick Add button, enter the number of carbs, and confirm the insulin bolus rate applied. The whole process takes less time than this sentence. For a more detailed look at lifestyle trends, each data type has a customizable box plot to identify patterns and plan actions accordingly. Observations from these graphs can be quickly written down in our application so no insight is ever forgotten. Using the default prediction or cloud-based neural network model, future ranges of blood glucose are forecast to instantly bring attention to potentially dangerous situations in the near future. Constantly listening to customer feedback during development, Tidemark is an amalgamation of features designed specifically for type 1 diabetics. This isn't hypothetical. Tidemark is a solution already measurably improving type 1 diabetics' lives. The only question is, are you ready to change the tide?
It's a nice marketing video, too. So as a technical overview, what exactly is Tidemark as a system? It consists of the iPhone application and a cloud-based backend. And these can be neatly tied up in 4 distinct categories. There's acquiring data, storing data, displaying data to the user, and predicting future data, future ranges of blood glucose. And we're going to be going in depth in each of these categories, starting with acquire.
For data acquisition, we wanted to ensure that our users can get data from a variety of sources. We've integrated with the Apple Watch to get heart rate data into our application, and for step count and blood glucose, we've used the Apple Health app. We've also created a basal insulin table to just similar to the insulin pump to directly put that into our app.
We also integrate with Fitbit for heart rate and Night Scout for blood glucose. If a user doesn't have any of these features or devices, they're able to manually enter data using the Quick Add button, which was developed in tandem with type 1 diabetics to make it as easy as possible for them to enter important information like meal data.
So we designed the display component of our application with simplicity and ease of use in mind. To start, on our dashboard, we highlight the most recently collected data points for quick access. If the user wishes to view their day-to-day data, they have 2 different options. One, they can, if they are looking for quick insights on their immediate trends, they can scroll to the bottom of the dashboard where they find their main graph, which is a display of their accumulated raw data. If they have more time to sit down and learn a little bit more about their trends in depth, they can visit the subpages of each data type where we provide more of an overview analysis.
So when data comes in from our devices, it's first stored locally and then pushed to the cloud. Also important to note is that the data is encrypted all the way through.
And as for the prediction side, we implement two models right now. We have the local prediction algorithm and a cloud-based model. The local prediction is fast and automatically displayed. The cloud-based model is extremely accurate. The results for both is the same, which is providing an easily identifiable way to see if preventable measures should be taken to avoid unsafe blood glucose levels. If you see that the prediction is going straight down or straight up, chances are you should take a second look and try and address the problem at hand. So how does it work in the field? It's been in the field for a month with our 3 trial users who very happily agreed to test our software. It's Bruno, Amber, and Zach, all from different backgrounds, all using different hardware, all integrating with our application, and they're all happy with the installation. We've been developing it with their feedback in mind, and they really feel like our application has helped them better manage their condition. But that wasn't good enough for us. We wanted hard numbers. So with one of our users' test data, we took back until the beginning of the school year, up until a month ago, and then the month ago from yesterday, all their blood glucose levels from those 2 time periods. We took the mean, the standard deviation, and the mean dropped 14 milligrams per deciliter down to safe ranges of blood glucose within 80 to 130 milligrams per deciliter, and the standard deviation, the variation, is less. And ultimately, at the end of the day, this leads to them feeling better and being safer as they live their daily lives. So Tidemark is here. Tidemark works. The only question is, are you ready to change the tide? Thank you. Questions?
There we go. When you're learning the models for each individual, did you account for variability in those models, and are they tuned to those people using them?
Yeah, good question. So the question was, how are the models tuned to individuals? So we looked at several different ways of approaching our prediction model. Locally, it's a prediction model that works in general for any user, which is a very general algorithm. In the cloud, I'd be happy to, if you'd stop by our booth, I can explain it in further detail. But basically, there's a prediction model that's trained on at least a month of user data. So they use it for a month, they get in all this data, and it uses a neural network model with about 90 inputs and 1,000 hidden layers to personalize their prediction to their data.
So how is is the main feature of your app sort of the predictive model? Because an Apple Health app has a graph that I can look at that kind of does that. Mm-hmm. So I'm sort of wondering where the main feature of your product is.
Yeah, good question. So what is the main feature of our application? Is it the predictive model? Is it the graphs? So I think of it is both. So the predictive analysis is to prevent unsafe levels of blood glucose. If something is going really wrong, you can tell immediately, and then you can take action against that. The graphs, however, we've gotten some great feedback because we integrate with everything that's important. So Health App leaves out insulin data, so you can't view your insulin data in tandem with the rest of your information. So really the ultimate goal was to put everything that our pancreas gets for information into this application, so it's a fair fight. And also in the data subpages, you can find box plots of your average values and your standard deviations, your min and maximums at different times during the day over the week, so you can start to analyze trends as well. So there's those three main features basically.
So it's a more targeted version of Apple, of that type of data. It's
essentially
more summarized and better presented, basically.
Yes.
These two answered two of my questions. So my last one that I wanted to ask you, particularly on encryption, and you guys talked about that a little bit. How do you broker connections with my data? How do you, someone else is going to hold it? Like you said, you upload it to the cloud. Yes. Do you see it? So if I use the app, can you look at my data? Can anyone look at my data?
Right. So how does the encryption work, and who can see personal data? So on the iPhones have innate encryption with a passcode. As it gets sent up it's through a secure protocol, HTTPS, so that's all encrypted. And we're using Azure as a backend, and so there's a default encryption there. So at the end of the day, during testing, we can see user data because we need to verify the results that we got. But when it's in application, if someone is spying on the cloud, they're just going to see gibberish.
So it's protected in transit, but then it's decrypted for people who have admin access to each of the databases, right?
As of now, yes. Okay. As of now for testing.
Cool.
Yep.
Why did you choose to store it in your own database as opposed to integrating with the health apps that are on the phone to store the data?
Because why are we using our own database as opposed to integrating with other databases? It's number one is it was a lot easier to manage the data. Number two is that we're using more data than they store if you're referring to Health App in particular,
yeah.
HealthKit. Yeah, we're storing more data than they support with their hardware interfaces.
Okay.
So yeah, insulin in particular, we're collecting more data, so we have to set up our own database locally and then our own database in the cloud as well.
Okay.
Are there already pre-existing standards for the way that you're collecting the data? I know some people were manually entering it, but other people, they had pre-existing products that they were using to either the pumps or to measure their glucose levels.
Yeah. So are there standards for how diabetics collect their data right now? So there's two components that type 1 diabetics have on their person. It's a way to monitor their blood glucose, whether it be continuous on their body. Dexcom is very, very popular for that, as the majority of the market share. And the alternative to that is just taking a finger prick measurement, which you just prick your finger, put the blood on a test strip, and you import it into some system. And there's also the way to deliver insulin into your body. And there's a lot of different ways to do that. There's Tandem. Zach has Tandem. Bruno has a different system. What does he have? Medtronic for him. So there's no standard way to do it in the industry. And that's one of the features of our application, is that we've included the ability with the quick add button to, if your application, if your hardware isn't compatible with ours, you can add it manually as well.
Okay, so if there are any more questions, can we hold those off till the demo session to avoid keeping us on schedule? So thank you very much.
Thank you.
Okay, our next team in this session is team number 8, Groove Gloves.
All right. Good morning, ladies and gentlemen. My name is Fritz Jolvin. That's Daryl Johnson, E. Liu. Right behind me is Brett Moretsky, and we have Richard Nesbitt. We are Team 8 Haptic Music. Our customer is Pauline Pisano, and the name of our product is Groove Gloves. So just a little background about why this project came to be. There are approximately 1 million deaf people in the United States. This includes both people who were born deaf as well as those who progressively lost their hearing. And our solution to that was to create a wearable system that converts music into vibrations, because these people have never had the opportunity of experiencing music like we do on a daily basis. This is intended for the deaf and hard of hearing community, like I mentioned earlier, and it gives the user a unique sensory experience all their own. So this is a top view of our final product, and this is a side view as well.
Here's a closer look of each part of our system. On each glove, there are 4 transducers on fingertip. And on the back of the glove, we fixed the amplifier board using Velcro. And we have an armband paired with each glove, and there are 2 pockets in it. And we have the Bluetooth module inside, and the other pocket is for the battery.
So what you just seen is the final state of the Groove Gloves. They are a pair of gloves that vibrate at the fingertips, where each finger represents a different frequency band, so that when you're listening to music, the different fingers let you interpret the music in a different way. The left hand receives audio input meant for the left ear when you're using normal headphones, and the right hand receives input meant for the right ear. The music input is any device that can connect via Bluetooth. And then we also have a smartphone application that can live stream audio of your surroundings so that you can feel what's going on around you. And what we're going to show next is a quick video of the final state, which is what you just saw. We're going to showcase how easy it is to connect to the device. Unfortunately, it's difficult for you to actually hear or see what we're sensing when you're using the device. So you're going to have to try that out manually, but we play music so that you can get a sense of what's actually going on.
So our product can be broken down into 6 core components. The first of which, and arguably the most important, is the transducers. And these are the devices that actually convert the electrical signal that our circuit board is producing to a tactile one that you could feel. We also pair that with a couple of amplifiers, specifically the LM386L and LM380N from Texas Instruments. Now these amplifiers actually amplify the electrical signals from our Bluetooth module to a level that can be felt by the skin. So now that we have a way to actually feel these signals, we actually just needed a signal to be felt. So to do this, we use two BC127 Bluetooth modules, one mounted on each glove, and each of them is running the Melody 6 firmware. So these Bluetooth modules would allow us to connect any phone that has Bluetooth and convert that signal into an audio signal that can be modified by the PCBs. So these PCBs need to be small enough to fit on the back of the hand, and they also need to be sturdy enough to mount all of the components that we had on them. They also provided interconnects for all of our components so that they can work together. Finally, we have the battery and armband. So for the battery, we use an Ankler E1 5200 milliamp hour battery, which as far as we can tell will not drain under normal use. It's an excessive amount of battery life for something like this. And to mount that, we use an armband to mount everything that couldn't be fit on the back of the hand. So to get this project off the ground, we needed to do a lot of research to understand how the skin feels vibrations. And by doing this research, we were able to map the vibrations that your ear picks up to sensations that your hands could pick up. Additionally, this research provided technical requirements that need to be fulfilled in our final design. And I also worked on the crossover and amplifier circuit boards, which would take the audio signal from the Bluetooth module and bring it up to a level that could be felt by the skin and modify it so that it fits how the skin feels vibrations better.
So there are no wires between the two gloves, so our device is truly wireless. So I worked on the Bluetooth subsystem of the device. So I researched, configured, and then tested our Bluetooth system that can work either independently, so you can wear one glove, or you can wear both to get that full stereo experience on both hands. And then I also worked on user-friendliness to design some ribbon cables so that when the user plugs it in, it'll prevent product damage. And then I also organized them to be less intrusive, that you can move your hands around.
So we split the power supply into two equal voltage sources. And originally, the voltage source is 5 volt. We used a voltage converter to boost from one source from 5 volts to 12 volts. And the 5 volts is for the Bluetooth module, and 12 volts is for the amplifier board. In this way, we can power the entire system using just one battery. And also, as mentioned, we have the armband for each arm, which increases the wearability, so you can easily wrap it around your arms.
A goal of our product was not only to convert pre-recorded music to vibrations, but also live music to vibrations for if our user is at a concert or just wants to hear the world around them or feel the world around them. So to accomplish this, I built an Android application to simultaneously record live sounds and send them to the gloves to be converted to live vibrations using the phone's microphone. The application also assists the users in connecting to Bluetooth and getting their device set up for the less tech-savvy users. I also worked on our power source selection to make sure we had a small and compact battery that could ensure portability for our system.
So with all of these components coming together, the final thing was to actually put them onto the glove. The way we did that is we actually glued the transducers to each fingertip on the gloves, with the thumb being free so you could still operate your phone. And then we have the amplifier and crossover boards mounted on the back of the hand using Velcro straps. After that, we have two components stored in the armbands, and those are the Bluetooth module and the battery.
We tested our device with a deaf volunteer from BU's Deaf Studies program, Bruce Bucci, and he compared the device to the feeling you get when you play the piano when we tried some classical music, which is definitely something that we're going for when we had the goal of converting melodies to vibrations and not just the bass. And that's one of the things that sets our device apart from the other similar products on the market that provide vibrations, in that most of them focus only on the bass, when ours converts the entire audible range of frequencies to vibrations, including melodies and vocals. So our volunteer was able to feel the vocals and musical instruments and confirm that. So we think that we We think that some future development we can work on is to reduce the size and cost to make it even more portable and comfortable, and increase the bass sensation, as Bruce suggested, since it's a good feeling to have that strong vibration in the bass. Thank you.
What was the process like when you had to extract or do some digital signal processing to get the different instruments and assign them to different motors? If you could speak to that.
So initially we were thinking of actually running the signals through a DSP, but after we concluded our research, we found that it would be much simpler to just implement it through a series of crossovers, pure analog, for the entire system.
I don't know, I might have missed this or not, but you said reduce size and cost. What was the cost for the entire system?
So all the components that are mounted on the glove came out to around $250, which is a lot for something like this. If you had like mass manufacturing and minimize the size, you could easily get this down below $100.
Did you experiment with anything other than gloves for the transmission?
So we were initially thinking of doing a vest, but our initial research showed that you want a high density of mechanoreceptors underneath the skin, and outside of a few parts of the body, your fingertips are essentially the most sensitive part. So to provide, since it is entirely a sensory device, we want somewhere that has a lot of sensors, which is why we ended up going with the hand. Though, as Bruce was suggesting in the video, he really enjoyed the full body bass experience that he's had in the past, which is why that'd be something we'd be looking for or looking towards moving forward.
And so the choice for the gloves was driven by the volunteer?
By our initial research. It was only until later in the project that we were able to test with a volunteer when we actually had like a working system.
Oh, okay.
And the
So you said you do like live streaming of just the environment to the gloves, right? What's roughly like the lag between like me speaking and them feeling it?
There's about a half second to a second delay in that.
What's the so the intensity for each finger? It is both the frequency like a pot of frequency ranges, and then it's also the intensity in that range. Is that the way to understand it works? Okay. Yeah.
You can also change the intensity by lowering the volume or raising the volume on your device.
That is something we are seriously considering at the start of the project, which would also require using a DSP or a similar microcontroller to do that. But we found through our research that you could actually feel transients at higher frequencies, so changes in amplitude at those higher frequencies. And by sort of emphasizing those higher frequencies, we put ourselves in a situation where we didn't actually need to frequency scale to feel information at those higher frequencies, even though the frequencies themselves are hard to feel, if not impossible, at those frequencies.
All right, thank you. Okay, the next team is the second of our student-defined projects this year. So this is team number 18, Rock Bands.
Hello, my name is Nick. This is Avi, Shika, Doug, and Yogi, and we are Team Rock Bands. So all too often, going to the gym, especially for beginners, is pretty stressful. You don't want to hurt yourself, and you don't exactly know what routines and exercises to go through to really make the experience efficient and definitely a positive one and a safe one. So here's a video describing basically our system.
Welcome to Rock Bands, your very own virtual fitness trainer. We have made it easier for newcomers to have a safer and more positive gym experience, with educational information for a variety of weight-intensive exercises. We have taken a revolutionary approach to simplifying working out and providing useful, real-time feedback for you, right through your headphones. I'm going to walk you through a simple bicep curl routine. All you need to do is select the parameters of your workout, your preferred weight and reps. Next, you're off to it. The real-time feedback reflects your form during your exercise. Here you can see the accurately detected alternation between twisting motion and the traditional straight arm curl. And now we have completed our set. Your exercise progress is now apparent on the routine page. Welcome to Rock Bands. Thank you.
So I'm going to hand this off to Doug for a technical overview.
So our system consists of three main parts. On the hardware side, we have two different things. The first is an IMU, which gives us linear acceleration, orientation, and direction of gravity. Connected to the IMU is an Intel Edison, which has software written in Node.js and communicates over Wi-Fi. The second part is a mobile application, which is an Android application. And the third part of our system is two machine learning algorithms, which are both neural networks implemented in TensorFlow. They are trained offline and then used online in our Android application.
Hi everyone, my name is Yogi and I'll be going over the hardware for you. So our hardware basically consists of three main parts. The Intel Edison, as Doug just talked about, as the microprocessor. The BNO55 sensor and the custom PCB that we designed using EagleCAD. So we're going to go over the custom designed PCB. We designed it basically to be able to use the Intel Edison and the BNO55 sensor at the same time while powering everything adequately. So as you can see, there are multiple LEDs to indicate the different states of the device, such as powered on, off, when it's resetting, when it's charging, and when it's connected to the mobile app. It also has multiple ports where you can input various devices like the Intel Edison, a lithium-ion battery, and also a micro USB cable to recharge that lithium-ion battery. So underneath the PCB is where we're going to put our lithium-ion battery, and the battery we chose was a 3.7 volt, 1200 milliamp hour lithium polymer battery. So we chose this particular battery because of its compact size, its lightweight, and its ability to hold enough charge to basically power the device for 2 to 3 hours, which is basically how long a typical workout would last. And then all of these internal components will go into a 3D printed case. Basically what the case is for is to protect the internal components from like potential collisions and any impacts that it could take. And then this is what we're going to refer to as a module. And these modules will basically go onto a couple of wearable gear, one wearable wrist wrap and one wearable belt. And this provides a secondary purpose to basically provide extra support to the user to prevent further injury.
So since this was a student-defined project, a lot of like the beginning was a lot of the first portion of the project was to just define what we really wanted this system to look like. So so we wanted you know the two modules, the wristband and the the belt, so we could provide two reference points for the machine learning algorithms, and then afterwards I transitioned over to like wireframing and UI design with Nick, and then towards the second semester we were trying to transition over from Wi-Fi communication to Bluetooth. But I got it done kind of late in the game, so like we didn't want to like start introducing. We didn't want to integrate it, and like start introduce and whatever bugs would come with it. You know, but like in a future like implementation, we would like obviously like integrate it with the system.
So for this part of the project, I worked on the authentication module that allows Rock Band users to connect their existing profiles with our application. Through this, the application creates a unique profile for each user. It enables them to save and track their progress. It also allows the users to view their analyzed metrics after their workout. Nick will tell you some more about the implementation of our mobile app.
So I worked on the user experience and the user interface for the mobile application, as well as the data structures to handle the logic and behavior within the application regarding the different features and things. I don't know if you can see from the picture, but there's actually it says today's rock level. So if you're feeling kind of wimpy that day, you can select a less intensive workout, but you could also go into beast mode as well, and we'll bump up the intensity for you. So it's, you know, third-party integrations and things like that, as well as like data flow and data-driven UI and the architecture really for the application to flow. And yeah.
So the first thing I worked on is the initial module prototype, and I wrote most of the software for doing the Wi-Fi communication. Once that was finished, I created a completely separate data collection application, which is shown on the right, and we use that to collect all the data that we would then use to train the algorithms. So that's the third thing that I worked on, is two different algorithms. The first is a rep detection algorithm, which basically detects when the user is doing a rep and when that rep is finished. And then the second algorithm is a rep classification algorithm, which basically once the rep is finished, it classifies whether the rep is good or bad and what the motion was.
So to give you an overview of what we've achieved so far, our system so far aims to help beginners lift weights, and it includes videos and step-by-step instructions on various basic movements such as bicep curls, bench press, and so on. So far we've been able to give you a proof of concept of a bicep curl. And it's able to automatically count reps for bicep curls, and it's able to detect the rep motion of a bicep curl and give you feedback on the movement to tell you if it's a straight curl or a twist curl. So the future works for this would be to further reduce the size to make it even easier for someone to wear the device and not have any obstruction during workouts, to add more exercises to the library, to expand the types of feedback it can give, like maybe you're rocking too much, or like you're any imperfections in form, and to generate exercise routines based on past performances to ensure that you progress over time with your fitness goals. We believe that this type of virtual fitness trainer has a huge potential out in the market, especially with a growing fitness industry and the rising prices for personal trainers. So yeah, thank you. We're Rock Bands, and we're here to help you crush your fitness goals.
The way it works is we actually pre-train the algorithms with our own data, and then when the normal user is using the application has already been trained. So there's no training period for a normal user.
Yeah, so to give you an example, to train the bicep curl that we can prove, we had all of us do like 200 reps each to like basically get it up and running. So now it can detect what's a straight curl and a right twist.
So anyone can come in and do a curl and it'll go. Okay.
You should be able to do that.
Yeah.
I feel obligated to ask, have you heard of Atlas Wearables?
So our main differentiator is like we do real-time feedback.
Oh, okay.
That's definitely what's unique to our particular system.
We're also aimed at beginners, so the whole teaching aspect is a main part of our.
Okay.
What was the total cost of this?
So for an individual PCB, it costs us to populate it and to order it after designing everything. It costs us around $60. The Intel Edison was around $50, and the lithium-ion battery and the sensor were about $20 each.
But we can also reduce costs additionally by using a less extreme chip.
Yeah.
The Edison.
Yeah, so like I mentioned, this was just to give you a proof of concept that it can actually give you real-time feedback. Like while you're doing a bicep curl, our app will actually tell you like twist, straight, and twist, straight, and so on. So like later on, we're gonna implement like imperfections in form. So like if you're rocking, then it should be able to tell you at which point you're gonna started rocking or whatever.
Maybe I missed this, but I was wondering if your system will be able to detect the difference between a rep curl and a bench press, or do you have to set that in your app?
So we focused on one exercise with two different types of motions. If we wanted to add more exercises, we'd have to collect more data and train a different model for that.
Also, when you're going to be doing a bicep curl, you have to go through the app to get to the bicep curl exercise. So it'll know what to look for while you're doing it. So if you're potentially going to be doing a bench press versus a bicep curl, you would be selecting the bench press, and then it would look for a bench press.
Thanks.
Right. So far we used the bicep curl, so we only demonstrated with the wrist. But we're gonna be implementing the belt as well to allow further movements like the squat or the overhead press, because the lumbar flexion is one of the biggest problems that beginners can make. So yeah.
Well, one thing that surprised me, well maybe not, when I tried it, they set the thing up for whipping, so I don't know what that is. Professor Al Sheikh, I think they set it up for beast. They flipped it actually just to make me feel good. All right, thank you.
Hey guys, catch!
Okay, we have one more presentation before lunch. So this is team number 24, 3T or Trivia Throw Toy?
Okay. Hi, everybody. My name is Jacob. This is Neil, Urvashi, Christine, and Charles, and we are Team Trivia Throw Toy.
Hey guys, catch!
The hump of the candle can weigh up to 35 kilograms.
Wow, what a neat fact.
How many facts are there? They're unlimited.
How is that possible?
From the World Wide Web.
Whoa. This connects to the internet?
Yeah, it does. I can show you how to do it. First, you click the Wi-Fi setup button. Take your phone and connect to the Trivio's network. You can go to the Trivio app, select your specific Wi-Fi network, enter your password. And the green LED means that it's successfully connected to the internet.
Hey, what are you guys looking at?
You just missed a cool fact this toy played.
Oh no. It's gone forever?
No, he didn't miss it. You can actually look at the fact history on the app. When you go to view fact history, it shows you all the facts you've heard before. You can also select a fact and give it a downvote or an upvote. What would you like?
Definitely upvote.
And it's also rechargeable.
Alcohol beverages have all 13 minerals necessary for human life.
So yeah, that's our toy. What it is, it's a ball-shaped toy that you can play with your friends, and it says fun facts that are pulled from the internet. What we tried to do with this toy is integrate the physical stimulation of playing catch with the mental stimulation of learning something new. We're trying to encourage people to interact with each other. They could use it as icebreakers, also motivate people to improve their knowledge, and just use it as a toy when you're bored.
So this is our completed product. It's coated in a shock-absorbent material to protect the hardware inside. So when you throw it or shake it, everything will be fine. There's a mini USB port for a rechargeable battery, so you don't need to take it apart and replace any batteries. There's a volume up and down button. There's a Wi-Fi setup button, which you saw in the video, will help you set up the Wi-Fi using the mobile app. There's also an LED, which, depending on the color, will display the status of the toy. The statuses include Wi-Fi setup mode, if it's connected to the internet, if it's not connected to the internet, and if it's low battery. We also have a fact history page where you can upvote and downvote. So this helps the server to know if a fact is fun or not. And if there's a lot of downvotes, then we can just remove it from the server to improve the user experience.
So this image shows the technical overview of our Trivia Throw Toy. There are 4 main parts. We have a phone application that's supported on both Android and iOS. It's used to create user accounts, retrieve fact history from the server over HTTP, and is used to set up the Wi-Fi credentials by sending it over to the toy over TCP/IP. We have the toy. It has a Arduino as a microprocessor inside. It has a PCB that hosts all the other modules together. The toy also receives the Wi-Fi credentials from the app over TCP/IP. The toy also connects with the server to retrieve the facts and download it stored locally for offline usage, if, like you can use it in the park or like outside. It also does that over HTTP. The server basically has a database hosted on Azure, and it stores user accounts, the data, the facts, and like the upvotes, downvotes for each fact. It also has an algorithm that parses trivia facts from the internet.
So I worked on the microprocessor code for detecting our throw or shake. We have an accelerometer which will pull values, and then if the difference between samples are higher than a certain threshold, it will detect a throw or shake. We have an SD card, which have 16 gigs of storage for storing facts for offline use. It'll also keep track of which facts have already been played. So then once it connects to internet again, it'll send those facts, which facts IDs over to the server, so we can replace those facts. To decrease latency when throwing the fact and throwing the toy and playing a fact. We play the fact from the SD card first, and then we go to the server to make the request for a new fact, which will replace that fact. So you don't need to wait for it to make a request and have a delay. I worked on the Android application. I also worked on the phone side of sending the Wi-Fi credentials. So how that works is that you connect to the phone's, to the toy's Wi-Fi that it emits. And then once connected, you go to the app. it will, using a handshake system, verify that's connected to the toy, and then it'll allow you to go to the next page to select which Wi-Fi you want to connect to, and then you enter in the credentials, and then once you click connect, it will send those credentials over using socket connection. I was also responsible for making the 3D model of the toy and the button and LED controls.
So I worked on the iOS application as well as the connection between the toy and the server with the Wi-Fi module. So how the phone application works is you register with your username, an email, and a password, and then it connects to the server, and if it authenticates correctly, it pulls that data in and then stores your unique user ID onto the phone's application. From this unique user ID, it starts a phone session, and then that's how the application and the actual toy are able to stay in sync. From the mobile application, you can manage your Wi-Fi as well as view your fun fact history, and that sends your user ID to the server and pulls in all the facts that you've heard. And as shown in the demo video, you can click on a fact and be able to upvote and downvote, and this way you can crowdsource opinion on facts that are good. And then for the connection between the toy and the server, it was an ESP8266 Wi-Fi module. And what it does, you have to configure it so that it sends post requests to the server when a fact has been played. That way, because of the cache, you know that a fact has been played, and then you can get it from your mobile app on the history table. And then it also has to be able to parse the facts by pulling in a fact from the server and then storing that into the cache.
So I worked on parsing the string as to vocalize it, so when the toy is shaking, you actually hear the fact. For that, I used a text-to-speech module called the EMIC2. You basically give it a string, and it makes it audio, and you can control the volume, the rate at which you want to hear the words spoken, make it faster, slower. You can also choose different voices. They have female voices, male voices, different accents, and all. I also worked on the toy part of receiving the Wi-Fi credentials. As Christine mentioned, there's a TCP connection that goes on a server hosted on the mobile application. The Wi-Fi module can be in AP mode, which emits its own Wi-Fi. So it also knows when a device is connected to it. So once the toy gets that connection, it tries to make a TCP connection over a certain port to it. And through that, a handshake system happens, and the credentials are sent over. I also worked on designing the PCB because the toy is going to be shaken or thrown a lot. So we need solid connections. It needs to be compact so you can hold it. It's more like a small football size, as you saw on the thing. And I also worked on detecting the battery level so that the user can be notified when it's running low, so charge it on.
So the toy is powered by the 2600 milliamp hours rechargeable battery. The batteries provide the toy for at least 3 hours to 4 hours usage life. And we use micro USB charging module to charge the battery. So the LED on the charger module will tell the user if the battery is fully charged or not. So it usually takes 1 hour to fully charge the battery. Since every part inside of the toy is vulnerable, like modules and the PCB board, so we use EVA foam as our protection for the surface. EVA foam usually used as yoga foam, because the material is soft, impact absorption, and soft is usually did a very good job to protect the toy and very comfortable to hold.
So the basic premise of our toy is that you'll never run out of facts, and in order to achieve that, we had to generate a database of trivia. And I created an algorithm which once it takes any website's base URL as an input, and it's able to output a bunch of facts on that particular website and its subsequent web pages. And we store this in a SQL database on Microsoft Azure. Additionally, we have a lot of functionality like creating users and voting on trivia and so on. So we needed a server and an API for that. So I created an API using ASP.NET. And the reason we have the voting functionality, like we said, it allows us to crowdsource the good facts and the bad facts. And we have the device. If you log in from a different smartphone, it already knows which facts you've heard, so that those facts won't play again. And similarly, the toy also talks to the server to essentially update it about which facts it has played and get a new fact when it's out of facts, essentially. So in conclusion, the way we've designed it, without any changes to the hardware, we can configure it for different use cases. So we imagine a scenario where if you want to cater it to kids, all you have to do is just change the type of facts they're receiving and configure the user accounts accordingly. So we have to do that on the server side, and with no changes to the toy, we can use it in many different scenarios. And we already demoed how adults like us would use it in our couch. We're just sitting and just throwing it around, and it's fun. So, yeah. Any questions?
Thank you. I appreciate the educational element here. I'm wondering if you guys can elaborate a little bit on what the up and downs mean. So is that like, this fact isn't true? I think I'm getting more towards fact verification and all this fake news.
The up and down
stuff.
fact. What's the purpose of the up and down
facts?
fact? So we're pulling facts in from the internet. We actually don't know what they are. I mean, we know like that it's a fact by the websites we choose, but we don't necessarily know that it's a good fact because there's like 5,000, there's like 10,000 on there. So we're using the opinion of the people who are using the toy to be like, oh, that was a bad fact or that was a good fact, to create better facts for other users. Like if a fact gets like a certain amount of downvotes, it'll get taken off the server.
So what websites are you using to get the facts?
So initially we were planning on using Wikipedia, but we pivoted to using a bunch of different fact collection websites which have trivia on their sites. And we also started using Twitter handles because there are a lot of them, which like Uber Facts, which start tweeting. So using Twitter's API, we were just able to pull data from their website.
So you can't use a random website like natgeo.com, and will you be able to?
We will, but we would have to configure it specifically for Nat Geo. So you have to enter the base URL, and we're algorithms looking for particular HTML tags. So websites tend to follow the same HTML tag for all the facts. So we can just pass information from there.
Cool, thanks.
Where's the text-to-speech actually done?
So there's a text-to-speech module. It's called the EMIC2. So basically, there's a library for it, and it works with the Arduino. So using the library, you can just like instantiate it and then send a string to it, and it makes it like an audio.
So it's actually done inside the toy itself?
Yeah, it's done inside the toy itself. Yeah.
If I throw the toy really far, does it save the fact mid-air, or does it wait till you cut?
Every time, like, it just detects a throw. So, like, for example, so the question was, if you throw the toy, like, in a long distance, when will it play the fact? When it posts acceleration values, that's when, if it reaches a certain threshold, it will play the fact immediately. So, for example, if you throw it really fast, it will play it basically instantly.
Yeah, there's a certain threshold so that if you're just walking with the toy, it doesn't get triggered.
I do. So these kind of, like, I have a follow-on question to kind of like your sourcing of facts and whatnot. Like, could I start gaming your server? Like, can I, like, do you have like any kind of like anti-spoofing or anti-tampering? Like, can I just like go and overflood your server with requests to say like the Earth is flat, and I convinced that this is a fact because I've upvoted it artificially a gajillion times?
So you set up a user account with your phone, and each user can vote only once on a fact. So to do that, you'd have to create thousands of user accounts, and if you're that dedicated, then sure.
Yeah, the Earth is flat. Like from the websites we're choosing, I hope the Earth is flat is not one of the facts that they have. But I mean, I guess you could create your own website that we might actually that has like fake facts on it.
I'll talk to you in 5 minutes.
Yeah.
I have to go make a website.
You guys talked about the foam protection on the outside of the ball. Is there any kind of protection for the hardware on the inside of the toy, or is it all on the outside?
So in the shell, there's a little tray which holds the PCB. So it will basically like hold it in place so it won't shake around or anything.
For you to use this toy, you can't. You need a Wi-Fi network. It has to connect. There are no facts that get cached to the ball.
There are facts stored like when you first get it, so like you won't have an instance where it'll say like you can't use it. But the thing is, if there is has never been a Wi-Fi network configured to it, the toy will say upon setup, please configure a Wi-Fi. It's 16 gigs, yeah. Yeah. We haven't tested that because we don't want to break our toy, but like we have tried dropping the toy without the stuff without the PCB inside, and it holds pretty well. It will play a fact. It will play a fact when for example, it will wait for a fact to finish. It won't so if a fact is being played mid-sentence and you shake it again, it's not going to cut off that fact. It doesn't cue it. You would have to shake it again after to trigger it.
Yeah, exactly what we were talking about, because it's very easy to just change the user account and the database, and we can configure it for different purposes. Professor Pisano actually wanted us to do it with ECE facts, so every time you throw it, it will tell you, like, ECE has 3,000 students and so on. Yeah. So we can configure it for many different scenarios. We were thinking of, like, multiplication tables for younger kids and so on. You could just keep going on. Just change it on the server side. Yeah, definitely.
All right, we are now at lunch. Okay, so the way you access the food is you go out through this door and take a right and another right and enter it from the hallway behind me.
Can I have your attention for a second? During lunch, we'll be passing around surveys for seniors to fill out. At the end of the day, today, we will have a raffle, and the 4 winners will get nice prizes. So please make sure you fill out either a hard copy of the survey or you've gotten an email with a pointer to the internet version of the survey. Thank you.